Good morning, class. Welcome to this session on refrigeration and air conditioning. So this is our first class and we'll be going through the basic concepts of refrigeration. Now, as you all know, refrigeration is actually the removal of heat from a material or space so that its temperature is always lower than those of the surroundings. Now, when the refrigerant absorbs the unwanted heat, it raises its temperature. Initially, it changes from liquid to gas, it evaporates, and then it again condenses to release the liquid and changes the refrigerant back into a liquid. So, there will always be a liquid known as a refrigerant that is used to extract this heat. Now, it is based on the physical principle that liquid extracts heat from the surrounding area as it expands into a gas. In order to accomplish all these processes, the refrigerant is pumped through a closed loop pipe, which this looped pipe stops the refrigerant from becoming contaminated and controls the stream of fluid. So the refrigerant will always change its phase. It will exist as a vapor and a liquid in the particular loop. Now, over the years history, there is a certain history to refrigeration. Initially, we had natural refrigeration wherein ice blocks were used. They were brought into rooms. The large tons of ice or large kilograms of ice, they were brought inside the room. They would absorb the heat from the room and it will melt away. So since during melting it will absorb heat from the room and produce a cooling effect. But this proved inefficient, so there was a development in the artificial refrigeration region. Now, the first known artificial refrigeration was demonstrated by William Cullen at the University of Glasgow in 1748. Since then, there were a lot of inventions. Prominent among them were being in 1805, Oliver Evans, who designed the first refrigeration machine. But the first practical machine was built by Jacob Perkins in 1834, and an American physicist, John Gorey, he redesigned Oliver Evans' design in 1884 and built a refrigerator based on it. Now, before we go into refrigeration, there are certain things that we need to, certain basics we need to clear. This is what you've learned in your thermodynamics, which is a thermal energy reservoir. These are bodies that have large thermal masses. That is actually bodies with large thermal masses can be modeled as thermal energy reservoirs, which is a hypothetical body that has a large thermal energy capacity. They can supply or absorb large amounts of heat without any change in temperature, which is most crucial. Now, a source is a thermal energy reservoir that supplies heat. A sink is a thermal energy reservoir that absorbs the heat. Now, this is the main law upon which we can explain the concept of a refrigerator and a heat pump, which is the Clausius statement, where it states it is impossible to construct a device operating in a cycle producing no other effect other than the transfer of heat from a low temperature body to a high temperature body. It states that in order to transfer heat from a low temperature to a high temperature, we need an external source or an external work has to be done on it. That is, in simple terms, a refrigerator will not operate unless its compressor is driven by an external power source such as an electric motor. Right? Now we go on to a refrigerator and a heat pump. This is what I've explained during the introduction part, that there is a refrigerant that is passing through the closed loop. You have a closed loop pipe system wherein there is a refrigerator. It will undergo two phase changing processes, that is from liquid to vapor in the evaporator and from vapor to liquid inside the condenser. Now, the evaporator is actually the freezer region that you see in our domestic household refrigerators. That is what is written here. The freezer compartment, heat is absorbed by the refrigerant, serves as the evaporator, and the coils usually behind the refrigerator is where heat is dissipated to the kitchen. It will serve as a condenser. So, evaporator is a freezer coil and condenser is what you see in the back side. This is the loop where it will exist as a vapor as well and a liquid. Right? So, the entire working we'll explain it in our further classes. We'll just be focusing on the simple basics. Now, again, the efficiency of a refrigerator is always expressed in terms of coefficient of performance or COP. Here, this is the figure. This is our refrigerator, which is used to extract heat from a low temperature body or sink and supply it to a high temperature body or the source. Here, actually, we define coefficient of performance as the ratio of the desired output to required input. In the figure, as you can see, what is the desired output? The desired output is to extract heat from the low temperature region, because we need to maintain this region at a temperature lower than that of the surroundings. Okay, so this is the desired output. Now, what is the required input? Required input is the work, because a refrigerator will work only if an external work is done or external power source is there. Right? So, desired output is actually QL, heat absorbed from the sink, and required input is actually the W net. Now we can also define W net based on energy balance equation as QH minus QL, that is heat supplied to the source minus heat taken from the sink. So again, COP you can write it as QL divided by QH minus QL, that is when you adjust the equation 1 divided by QH by QL minus 1. So there is an important question that comes into play. Can the value of COP of refrigerator be greater than unity? We will discuss. Now the second topic is actually a heat pump. The objective of a heat pump is to supply heat QH into the warmer space. Earlier our required or desired effect was to extract heat from this portion. Now in the case of heat pump, this is our objective or our desired output is to actually supply heat to warmer heated space. Now heat pump does the opposite effect that of a refrigerator, right? Its working is similar to refrigerator, but it does the opposite effect. That is, the heat pump always works and it performs it performs in a way such that it extracts heat or energy from the cold outdoor regions and carries it into the warmer indoor regions. So cold air at 4 degree, you can see the example here, it takes heat from this low temperature surroundings. External work is done on the system heat pump and it will supply heated or a certain amount of heat to warmer indoor regions. So the working is almost the same for both, but still there is a difference being the desired output. So again you can define COP of a heat pump as a desired output to required input, desired output being QH, required input being W in. So QH by QH minus QL, 1 divided by 1 minus QL by QH. Again, when you adjust the equation, what you'll get is COP of heat pump is always greater than COP of a refrigerator. Now, can the value of COP of a heat pump be lower than unity? We'll have to discuss the question. What does COP of heat pump equal to 1 represent? This is the difference between the refrigerator and the heat pump. You can see the difference in desired output: extract heat from the low temperature source, supply heat to the to absorb heat from the low temperature sink, and supply heat to the high temperature source. Now this is the last subtopic that we'll be discussing in today's class, which is the tonnage of refrigeration. It is the amount of refrigerating effect produced by uniform melting of 1 ton of ice from or at 0 degrees Celsius in 24 hours. Tonnage of refrigeration is usually as a value, that is 3.517 kilowatt or 210 kilojoule per minute. Now, tonnage of refrigeration, what it actually implies is, if you have 1 kilogram of ice or it's not 1 kilogram, I'm very sorry, it is 1 ton of ice or 1000 kilogram of ice. This ice, assuming this ice block is 1 ton or 1000 kilogram, it has to melt and completely converted to water by absorbing heat in 24 hours from or at 0 degrees Celsius. So the temperature has to remain constant, right, which is always there in the case of phase change process. So at 0 degrees Celsius and within 24 hours, this 1 ton of ice should be completely converted to water. That is what it represents. Now the latent heat of ice or the heat of fusion is 333.55 kilojoule per kilogram, or 144 British thermal units per lb. Now 1 short ton is equal to 2000 lb. So what will be the heat extracted? 2000 lb into 144 divided by 24 hours, that is equal to 288,000 BTU by 24 hours. Again, that is equal to 12,000 BTU per hour. That is again equal to 200 BTU per minute. So 1 ton of refrigeration equals 200 BTU per minute. Again, it is 335 kilograms. So in order to get 1 ton of refrigeration, 335 kilojoule per kilogram into, you'll multiply it by what? You'll multiply it by the multiply it by 1000 kilograms. So 333.55 into 1000 divided by 24 into 60. So what you'll get is 210 kilojoule per minute. This value you will get. That again divided by 60 will give you 3.517 kilojoule per second. So you have two units, BTU per minute and 3.5 kilojoule per second. Both of them are used to define ton of refrigeration, or the value is expressed in both terms, 200 BTU per minute or 3.517 kilojoule per second. This is actually the conversion. The only difference being 333.55 into 1000 divided by 24 into 60. So we come to the end of our class. I hope we'll discuss more and more in our upcoming classes. Thank you.